Okay, we've learned about Cauchy-Riemann conditions in the previous lecture. Now, it is necessary for us to look at analytic functions in more detail. So, we had introduced analytic functions in the previous class as those functions that obey Cauchy-Riemann conditions. In reality, however, the requirement for a function to be analytic is has more than just the Cauchy-Riemann conditions, and in detail it involves one, of course, the Cauchy-Riemann conditions. In addition to that, the function is also required to have its derivatives to be continuous, and finite at the points where we are interested in checking the analytic property of the function. So, Cauchy-Riemann conditions themselves form a necessary condition, but they are not by themselves sufficient to ensure that the function is analytic. In addition to that, we also require the function to be, the derivatives of the function to be continuous and finite for it to be an analytic function. We had seen a few examples of functions that obey Cauchy-Riemann conditions in the tutorials, and the simple functions such as f of z equal to z square, which is a monomial, or a, more generally said, a polynomial of degree 2, is one such example, which we have checked that it satisfies the Cauchy-Riemann conditions. It is also easy to see that the derivatives of this function is continuous at all points where the Cauchy-Riemann conditions are satisfied, and in fact they are also having a finite value at all those points. The derivatives have finite values. So, clearly these are functions that can be confidently termed as analytic functions. There are many such functions that we can indeed categorize as analytic, such as e to the z, and several functions. In fact, most of the polynomials that we know are analytic functions. It is important to remember, keep in mind that the analyticity that we talk about is most often done, or we term a function analytic referring to only a certain region of the complex plane, and a function is termed analytic in such a region. If I call that region D, a function is called, or a function is analytic in that region D only if the Cauchy-Riemann conditions are satisfied, as well as the derivatives of the function are continuous and finite in that region. So, these functions certainly have that property. In fact, these functions do much better than that. That if you take the entire finite complex plane, all those parts of the complex plane, leaving out the points at infinity, okay, for real and imaginary parts running to infinity, except at those points, for all finite region, finite part of the complex plane, these functions obey both these conditions. Such functions are often called holomorphic or sometimes also called regular functions. In this context, it is good to remember that if I take a constant, let us say f of z equal to 2. Now, that is also a function of z, it is a trivial function, it is a constant function, a function whose value remains just that. In fact, I need not take a real number, I could take I into square root 3, a constant complex number. If I take a function of this form, it is clear that this function, being a constant function, easily satisfies Cauchy-Riemann condition, and it also satisfies the second requirement that the derivatives be continuous. Of course, if you take the derivative of it, it vanishes, and its value is 0 everywhere on the complex plane. In fact, it is nowhere is it infinite, it is a finite value. Hence, it can be termed a regular or holomorphic function easily. However, for such a function, constant function, there is no problem that it faces even at points at infinity. Even at those points, these two conditions are never violated, and hence such a function is often called an entire function. Okay, so a constant function such as this can be said to be analytic on the entire complex plane, okay, not just the finite part, but including at the points at infinity. Now, it is interesting to ask what are the type of what are the ways in which a function can lose its analytic property in at certain points or certain region of the complex plane. Let us look at a function of the form f of z equal to 1 by z square, or 1 by z to begin with. Now, if you look at this, a function such as this, it is easy to see that we could check that this function satisfies the Cauchy-Riemann conditions at all points except at point z equal to 0, the origin of the complex plane. So, except at the origin of the complex plane, everywhere else this function satisfies Cauchy-Riemann conditions. If you look at the derivative of this function, that is also continuous and also finite at all points in the complex plane except at the point at the origin of the complex plane. At origin of the complex plane, you can see that if you take the derivative of this function, it gives us minus 1 over z square. At z equal to 0, it clearly becomes infinite, and thus it stops obeying the second condition, the second requirement for the function to be analytic. So, we can say that such a function stops being analytic at origin. When a function stops being analytic at a point, in this case at origin, we say that the function has a singularity. In this case, we could say that this function has a singularity at z equal to 0. So, we are going to see more examples of functions which have singularities at certain specific points. But before proceeding with it, let me point out once again that this particular function 1 over z has a singularity at z equal to 0, as we have seen. However, everywhere else except at the point z equal to 0, this function is completely analytic. It obeys Cauchy-Riemann condition as well as the second requirement of being continuous and finite, derivatives being continuous and finite. Before we proceed to understand more examples of singularity, let us observe one feature of this particular type of singularity. If you look at this singularity, it is easy to observe that if I multiply this function f of z equal to 1 by z with z, it gives me 1, a constant, which is an analytic function. So, multiplication with z, which can be in general called a polynomial, has helped me to remove the singularity which the function 1 over z had at z equal to 0. And the function z into f of z that we got, which is equal to 1, has no singularity at even at z equal to 0. So, such singularities that exist at certain points that can be removed by multiplication with an appropriate polynomial is often called a pole. Depending on the degree of the polynomial that you have to multiply with in order to remove that singularity, we say that that particular pole has an order, and if n is the degree of the polynomial that we multiply, then we say that the pole has an order n. In this case, of course, the polynomial that we multiplied is z itself, which is a polynomial of order 1, degree 1, and hence we say that this particular function f equal to 1 over z has a pole of order 1, which is also very often called a simple pole. A pole of order 1 is often also called a simple pole. Now, if you consider one more example, f of z equal to, let us say, 1 over z minus I cube. This function, as you can see, this function as well as its derivatives has a problem, has no problem at any point except the point at z equal to I. At the point z equal to I, the function blows up, function becomes infinite, and its derivatives also becomes infinite, and hence it loses its analytic property. Everywhere else the function is already analytic, and this particular singularity that the function function has at z equal to I can also be removed by multiplication with z minus I cube. Hence, and the order of that polynomial that we need to multiply to remove that singularity is 3. Hence, we say that this function has a pole of order 3 at z equal to I. So, z equal to I is a pole of order 3 for this function. So, mind this is the point z equal to I on a complex plane. It is a completely imaginary, on the imaginary line. Another example of a or another type of singularity that functions on a complex plane have are the ones that we can learn about by looking at the function, let us say f of z equal to square root z. To observe the singular behavior of this function, it is good to express the function in terms of in terms of the polar variables r and theta. So, if I write z equal to r e to the I theta, we can write this function as square root r e to the I theta over 2. And let me try to plot this function. Let me try to look at the complex plane to study the behavior of this function. Let us look at the value of this function at some point which is coordinates r and theta in polar form. So, let that be r and let that be theta, so that this is the point z equal to r e to the I theta. It is clear that this variable z will have the same value if I take this line joining origin and that point and rotate it about origin and bring it back to itself. When I rotate this line, or when I equivalently, if I carry this point and take it around the origin through a circle of radius r and bring it back to its original location, all that happens to z is that it goes to r e to the I theta plus 2 pi. When I go around the point, the angle increases by an additional 360 degree. However, since e to the I 2 pi is e to the I 2 pi is 1, we get back r e to the I theta, which is our original point z itself. So, this tells us that if you go around the origin and come back to the same point, this variable, you come back essentially to the same point. There is no change of point, or there is no change of location. That point has the same set of same coordinates when you get back, or when you go through a 360 degree rotation. However, now let us look at this function, which is the function of z. If I look at what happens to this function when I carry this point around the origin through 360 degrees, we can see that this function goes over to square root r e to the I theta plus 2 pi over 2, which if you simplify, you can see is square root r into e to the I theta over 2 into e to the I pi. However, e to the I pi has a value minus 1, giving us minus of square root r e to the I theta over 2. So, what has happened is that when you return back to the point after doing a 360-degree rotation around the origin, the function does not return to its original value, but changes value to negative of its value at theta. So, this seems to create a problem manifestly for the continuity of the function, that you are talking about the same point, however, the function seems to have more than one value at a particular point. So, such functions also are said to be singular or not analytic, and the singular behavior is identified with the point z equal to 0, around which we did the rotation through angle 360 degrees. We say that in this case the function has a branch cut singularity at z equal to 0. And now, it is interesting to observe that if I do a further 360-degree rotation, making it a total 720-degree around the origin, we get back to the original point. So, this function which seem to have two distinct values at the point z equal to r e to the I theta, is said to be multi-valued at this point z, and the multi-valuedness is said to be due to the branch cut singularity at z equal to 0. There are ways to deal with such functions or look at the same function as a single valued by abandoning a complex plane and introducing multi-sheeted complex planes, and which are called Riemann sheets, and so on. We will not see too many examples, or in fact possibly no example of branch cut singularities in this lectures, which has limited scope of learning the basics of complex analysis.